For those of you that don't know Glenn and know our products, he created the smoke test. He also created low profile venting, which I don't believe he sees a penny of royalties on that. Don't get any ideas, Glenn. But nonetheless, I'm very happy to have him. And he is going to be talking about diffusion testing through membranes, as well as some of the QA/QC or system verification testing that he presented earlier at AVIP back in October. So take it away, Glenn. Thank you.
Thanks for the introduction, Peter. I assume everybody can see my screen. I'll take that as a yes. So today I'm going to quickly talk about three different types of QA/QC testing for vapor barriers. I'll start with testing to evaluate chemical compatibility and transmission characteristics of the membranes. Then I'll touch upon quickly smoke testing. And last but not least, I'll talk about post-installation performance testing to establish soil gas to indoor air attenuation rates for the membranes. First topic, chemical compatibility and transmission rates. We've been measuring both diffusive and convective transmission across membranes since the 1980s, and have had tests running continuously actually since the 1980s in some cases. This is the typical test setup that you see here. We'll have a container, two halves, a solution of water and a VOC in the bottom container separated by a membrane, and then the upper container is connected to a series of activated carbon filters. So as the VOCs diffuse across the membrane are transported by pressure differential, which we can set up across the membrane, they're captured by the filters, and we can measure the rate of transmission and quantify that rate. It's a typical test setup. We've had to use larger and larger test containers over the years as the membranes have gotten to be better and more restrictive. This is a typical result, excuse me, that we like to see. Data points, falling on a straight line in a linear fashion. Our minimum test period, usually for this type of testing, is 120 days. We've had samples that have been running for years. What we don't want to see is, as time goes on, a higher transmission rate, which tells us the membrane is degrading. So again, Peter's for EPRO has a lot of data and can provide this. I would imagine anyone who wants to make sure the membrane is going to have suitable engineering characteristics so you can calculate risk assessment values. These are compounds we've tested, concentrations, and measured diffusion coefficients. The concentrations that we test these at are usually extremely high, in the millions of micrograms per cubic meter. So it's a very aggressive chemical compatibility testing environment. Installation QA/QC testing, these are all standard protocols. One of those is smoke testing, which is pretty critical. Typical smoke testing apparatus, non-toxic smoke like you might see at a concert venue, and a blower to pass the smoke through the vent piping and underneath the membrane. This is a 24-year-old photo taken during the early years of this type of testing, which started in the 1990s. Then and today, we typically lift the membrane off the subgrade during smoke testing, not typically as much as is shown here. This is somewhat exaggerated, but it's beneficial to do that to make sure we're getting smoke under the membrane everywhere. And it also relieves thermal stresses that tend to build up during the installation process due to temperature variations between night and day. So we found that to be very, very helpful. Before we started smoke testing membranes, installations of this size in a typical residence, we would inspect thoroughly and be quite confident that they were intact without any leaks. And then when we started smoke testing them, we would find 10, 15, 20 leaks in something this size, things that you wouldn't otherwise see. So it's pretty critical to run the smoke tests Just the process of doing that over the years has helped us reduce the number of leaks that we would otherwise have. The third and one of the most critical types of testing I'll talk about is post-installation performance testing. And the attenuation rate, the soil gas indoor attenuation rate for a barrier system is dependent upon both the characteristics of the membrane that you're using and the other components of that system, the ventilation components, and to a large extent, it's dependent upon the quality of the installation. You can take a good membrane and basically ruin it if it's not installed properly. The way we quantify the performance of a membrane is with soil gas indoor attenuation rate, which is basically the reciprocal of the attenuation factor that Andrew was talking about. I like to use the rate because it's an integer value rather than a fraction. And it's just defined as whatever the concentration of a particular compound of interest is in the soil gas divided by that concentration in the indoor air, and we subtract the outdoor air concentration because we're really just interested in what's getting across the barrier to the indoor air. We don't want to what's in the outdoor air to count against us. What we found that the VOC source concentrations at many sites are too low for us to measure the attenuation rate of a barrier using VOC data. And another problem in using VOC data for this measurement is that we've got a lot of contaminants on the interior of the buildings from construction materials and other things. So the compounds that are present in the soil gas are often present on the interior of the buildings already, especially with newer construction. And the third issue, in an urban area, we've got fuel hydrocarbons and we've got off-gassing from disinfection byproducts that we typically find in indoor air, and it's hard to tell what might be from soil gas and what's not. So because of that, we typically measure the attenuation rate of a vapor barrier using radon gas as a surrogate for VOCs. I would say in less than 2 or 3% of the projects we have are we able to measure an attenuation rate using VOCs. It's a very small number because the attenuation rates for these barriers are very, very high, and we typically can't find detectable levels of VOCs in the indoor air. That's the problem. Radon's a naturally occurring radioactive gas. There are 39 different isotopes. There are a couple that are most relevant. Radon 222, which is just called radon, is primarily what we're measuring. It's got the longest half-life of any of the isotopes at 3.8 days. Another isotope that's relevant for other reasons when we're tracing leaks or trying to find them is thoron. It's got about a 1 minute half-life. And I should point out the source compounds that generate radon gas have half-lives that are in the billions of years. So radon concentrations in the ground tend to be very stable because of that. Radon map of the United States, we found even in areas where the radon, soil gas radon levels are supposed to be low, we've got high enough levels to use radon as a surrogate. A lot of different detectors are available to measure radon concentration, some of them inexpensive, a couple $100, some of them more expensive. Some of these devices can distinguish between the different isotopes of radon, which can be useful. We found even these less expensive devices in the $200 range yield results that are comparable with the more expensive equipment. What we typically do, we'll have a gas probe beneath the barrier, and we'll measure the radon concentration in that probe. We'll measure it in the indoor air, and we'll measure it in the outdoor air concurrently over a minimum of a 24-hour period. Typical gas probe connections, we usually terminate them in the foundation stem wall. Typical results, soil gas levels up here, around 150, 200 picocuries per liter, indoor, outdoor air down here. And we measure the barometric pressure, and have a dropping barometric pressure curve like this is ideal because it tries to force VOCs to the indoor air. And for this data, we calculate an attenuation rate of just over 6,000. It's not unusual to find attenuation rates with a good installation of 10,000, 20,000, even 30,000, which compares to the 33, default attenuation rate, which is used by the state of California. So you can get very high levels. This is another test result, the passive system then being turned active on the right. One of the questions we're typically asked by regulators, okay, we can determine what the attenuation rate is at the time of construction. How do we know that's going to last? How do we know the barrier is not going to deteriorate? How do you know a homeowner's not going to jackhammer a hole in the floor slab of their home? And one of the ways to determine that, we've got a number of projects where we've installed these relatively inexpensive $200 monitors as part of the VIM system, and they will continuously detect and record radon levels. And we can download that data without entering the building as long as we're in proximity. Typical testing results, this red squiggly line is the indoor air radon level measured by one of those devices over time. It's a multi-year period. The green line is what we measured at the time the barrier was installed. And then we've got the barometric pressure up here. So we know our soil gas radon level is constant. So if we don't see a significant deviation of the indoor air radon level from that base concentration, we know we still have the same or a very similar attenuation rate. We can also look at the barometric pressure response and see if we're getting inflow through primarily diffusion or primarily convective flow. And that's my last slide.